Alrighty, guys, so we're going to continue on with talking about quadrilaterals. And today what we're going to talk about is we're going to look at proving that a quadrilateral is a parallelogram. Okay, so let me give an overarching idea of what we're doing today. So yesterday we said that these things were parallelograms, and because of that, some special things happened. Okay, specifically we had opposite sides are congruent. We had opposite angles were congruent. The same side angles were supplementary, and the diagonals bisected each other. Okay? What today is we no longer can say they're a parallelogram. We don't know that yet until we talk about these theorems. What I am going to say, though, is that these things have already happened. Like, this is just a regular old quadrilateral that just so happens to have opposite sides congruent. And we'll talk about what that means. Okay? On this one, it's just a plain old quadrilateral, but the opposite angles are congruent. And because of that, we can call it a parallelogram. Okay? These are in logic talk. What we're talking about today is the converse of what we talked about yesterday. It's kind of like saying it backwards. Okay, let's get through a couple, and I'll show you what I mean. Okay. So first thing, now what I would say to y'all is, for you watching this video, after I write the theorem down, pause the video so you can get it copied down. Okay, because I'm going to go kind of quick to get them down. All right. So theorem 6.5. If the opposite sides of a quad. Now just know when I say quad, I'm talking about the whole word quadrilateral. I'm just not writing it out because I'm lazy. Okay? So the if statement is, if the opposite sides of a quadrilateral are congruent, then we can say, then the quad is a parallelogram. Okay, and I hope you can kind of see the difference of how this was yesterday. Yesterday, I told you it was a parallelogram, and so we said that a property of it is that the opposite sides are congruent. Excuse me. Today, we're saying it backwards. We're saying if the opposite sides are congruent, then it is a parallelogram. Okay? All right. 6.6. If the opposite angles of a quad are congruent, then the quad is a parallelogram. Okay? Moving on. The third one, if the diagonals of a quad bisect each other, then the quad is a parallelogram. Okay? So these first three should be kind of familiar. They're the reverse sayings of what we talked about yesterday. This last one is new. It's a little bit different. What it says is, if one pair of opposite sides of a quad is parallel and congruent, then the quad is a parallelogram. Right? So these are pre-marked for you so that these arrows mean parallel. We talked about that. And then there's a tick mark to say they're congruent. So that's kind of a unique case there. If one pair of sides is both parallel and congruent, we can say it's a parallelogram. All right? All right, let's use these theorems. Okay, and as far as the work, it's going to be similar to it's very similar to what you did yesterday, but the thought process behind it is different. Okay, so we need to find the value of x for which JKLM must be a parallelogram. Okay, so at this point, we cannot say it's a parallelogram. We don't know that. All we know is that it's a quadrilateral. Okay. But what they've given us is they've given us a pair of sides and some expressions, okay? They want us to find out what the value of x needs to be so that we can force this to be a parallelogram, all right? I hope that thought process makes sense because it's different than what we did yesterday. Anyway, if we want this to be a parallelogram, what has to be true about the opposite sides? Well, let's see. If we want a parallelogram, then opposite sides must be congruent, have to be congruent. So, if we want it to be a parallelogram, we have to let this side be congruent to this side. So we're going to take our expressions. 7x minus 2, set it equal to 12x minus 22. Okay, and we're doing that because we want the opposite sides they must be congruent. Okay, now we solve it out. So always subtract the smallest x. It's just good practice to have. Then add 22. So 20 equals 5x. Divide by 5. We get x to be 4. Okay. As far as the actual work you have to do, that's it. I mean, it's not that much. It's not different from what you did yesterday, but it's the thought process that's different. I hope I'm making that kind of clear. All right. Find the value of x for which QRST must be a parallelogram. So at this point, we do not know it's a parallelogram. We just know it's a quadrilateral. What they've given us is a pair of angles, and in this instance, those angles are on the same side of the parallelogram. Now, we didn't say this per se yesterday, but I think you can figure it out. Okay, we talked about yesterday that if it's a parallelogram, then those angles on the same side are supplementary. Okay, so now we're going to do the flip side. We need these same side angles they must be supplementary. Right? If we want it to be a parallelogram, this has to be true. So what are we going to do? We're going to take 3x plus 5, add 9x minus 17, and equal it to 180. Combine like terms. 3x and 9x gives me 12x. 5 minus 17 gives me minus 12. Now add 12. Divide. And you get x to be 16. Okay? So if x is 16, then it's a parallelogram. If it's anything but 16, it's not a parallelogram anymore. It's just a quadrilateral. All right? Third one. We want ABCD to be a parallelogram. And so what they've given us is they've given us a pair of opposite angles. So if we want this to be a parallelogram, we have to have the opposite angles must be congruent. Okay, if we want a parallelogram, these things have to be congruent. They have to be equal. So we're going to set them equal to each other. We're going to solve. So move the smaller x. By 2. X is 13. So if our x is going to be 13, we're good to go. We got a parallelogram. If x is anything but 13, we do not have a parallelogram anymore. All right. Now, these are kind of like informal proofs, okay? What we're going to do is we're going to see if this information they gave us is enough to say that this is a parallelogram, okay? And I think what would help us is if we mark up the picture according to what they tell us, okay? So, angle SPX. So I like to follow those letters. S, P to X. Oh, you can't see it. Sorry. S, P, X. It has to be in between there, so that angle is right here. Okay, so make sure you mark yours up like mine. That is congruent to TMX. So TMX, which means this guy right here gets, oh, can't draw it right. One arc measure there, one little arc. Right? Now, they're also saying that TPX, so T to P to X. So what's this other piece over here? I'm going to give him 2 because it's a different angle. TPX is congruent to SMX. So SMX, so that's going to be that little piece right there. Okay? That's all they gave us. And so the question is that enough to prove this is a parallelogram? So let's stop and think. Does this drawing fit anything that we've talked about here? So sit and stare at it. And hopefully you figured out by now it doesn't fit any of these criteria. But there is something else we can use to prove it. We can actually use the definition of a parallelogram to prove this. Okay? So if you recall, a parallelogram is a quadrilateral that has two pairs of parallel sides. Okay? So if it's a parallelogram, then we have these two sides are parallel, and then this pair of sides is parallel. And so what's happening here is that we've got alternate interior angles here. Now, I know it's pulling back from Unit 3 of Geometry Part A, but we got to use it again. This angle marked with one arc and this angle marked with one arc. They are alternate interior angles. They are congruent. So it is forcing SM to be parallel to PT. And then on the flip side, this angle marked with two arcs is forcing the sides SP and MT to be parallel. And so because these groups of angles are parallel, it forces all your sides to be parallel. And that fits the definition of a parallelogram. So here we're going to say yes, alternate interior angles force the sides to be parallel. Okay, that's an instance where you use the actual definition to prove it. You might have to do that, so don't forget that definition, okay? All right, let's do the last two. SX is congruent to XT, so I'm going to mark that up. And then SM is congruent to PT, so I'm going to put two dashes for them. All right. Does this match anything we have here? It almost does. It's kind of like they combined half of this one with this one, half of that one. And so unless it's exactly like one of these or the definition that we did up here, we can't say it's a parallelogram. So we're going to say no. What do we need? Well, if we're looking at just the diagonal part here, we have one diagonal that is bisected. We need to know that the other one is bisected. So we would need to know that PX is congruent to MX. Or if we're talking about the sides here, we need to know that the other pair of sides is congruent. So we need to know that SP is congruent to MT. Either one of these would be enough to say it's a parallelogram, but we don't have it, so we say no, it's not a parallelogram. Okay, let's see if this works. So we're going to say that SP is congruent to MT. Oh, and by the way, these should have segment bars on top. I forgot to add those for you. I just realized that. Those are supposed to have segment bars. I'm sorry, I forgot to add that for you. Anyway, SP is congruent to MT, and then they're saying SP is parallel to MT. So we need to add our parallel symbol, which is our little arrows. Okay, now I'm going to look. Is that enough? to say it's parallel. So I'm looking through my kind of like my picture references. Hey, here it is. We have one pair of sides is parallel, parallel and congruent. So for this example, we're going to say yes, my theorem 6.8. So that theorem says that that's enough to be a parallelogram. Okay. All right, that is all there is to proving parallelograms, or proving a quadrilateral is a parallelogram. That's all I have. So please make sure that you watch this video in its entirety before you start on your homework. And if you have any questions, let me know.